Imagine a vast, dark cosmos. It's speckled with stars, planets, and galaxies. But hidden within this cosmic tapestry lies a secret world. It's a world of electric charges, positive and negative, constantly interacting. These charges are the fundamental building blocks of matter. They influence everything around us, even if we can't see them. Now picture these charges as tiny dancers. They're scattered throughout the universe, waiting for the music to start. When an electric field appears, it's like a cosmic DJ hitting the play button. Suddenly, these charges spring to life, aligning themselves with the electric field. This alignment, my friends, is the essence of electric polarization. Electric polarization is more than just a cosmic dance. It's a fundamental phenomenon that governs how matter behaves in the presence of electric fields. From the simplest atoms to the most complex electronic devices, polarization plays a crucial role. Understanding this concept is like unlocking a secret door to the universe's inner workings. In our journey to explore electric polarization, we'll uncover the secrets of this hidden world. We'll see how it shapes our understanding of materials and how it's harnessed in countless technologies we rely on every day. So, fasten your seatbelts as we embark on this electrifying adventure. So, what exactly is electric polarization? Imagine a balloon. Now rub it on your hair. What happens? The balloon becomes charged, right? It can now attract small pieces of paper. This happens because the balloon's surface becomes polarized. Electric polarization is the alignment of these tiny charges within a material. It's like a cosmic dance where the dancers are the charges and the music is the electric field. When there's no electric field, the charges are randomly oriented, like dancers milling about on a dance floor. But introduce an electric field and the music starts. The charges feel a force, causing them to align themselves with the field lines. Positive charges shimmy towards the negative end of the field, while negative charges sway towards the positive end. This orderly arrangement of charges is what we call electric polarization. The strength of this polarization depends on the type of material and the strength of the electric field. Some materials, like water, polarize easily, while others, like wood, are more resistant. The stronger the electric field, the more pronounced the polarization. Now that we understand what electric polarization is, let's dive deeper into how it actually happens. Remember our dancers? When the electric field kicks in, it's like an invisible force pulling and pushing them into formation. Picture a neutral atom. It has a positively charged nucleus at its center and negatively charged electrons orbiting around it. In the absence of an electric field, these charges are perfectly balanced, creating a neutral atom. But introduce an electric field and the balance is disturbed. The positive nucleus feels a tug in one direction, while the negative electrons feel a pull in the opposite direction. This causes the electron cloud to distort, shifting slightly away from the nucleus. This distortion creates a dipole moment within the atom. A dipole moment is simply a measure of the separation of charges. The larger the separation, the stronger the dipole moment. The atom, once neutral, now has a positive and a negative end, like a tiny magnet. This process happens to countless atoms within a material when an electric field is applied. All these tiny dipoles align themselves with the field, creating a net polarization within the material. It's like a synchronized dance of charges orchestrated by the invisible hand of the electric field. Section 4. The many flavors of polarization. A cosmic variety show. Just like there are different genres of music, electric polarization comes in different forms, each with its unique characteristics. These types of polarization depend on the type of material and how the charges within it respond to the electric field. First up, we have electronic polarization. This type is like a quick, nimble dance. It occurs in all materials and involves the distortion of electron clouds within atoms, as we just discussed. It's a very fast process, happening almost instantaneously when an electric field is applied. Next, we have ionic polarization, which is more like a slow, deliberate waltz. This type occurs in materials with ionic bonds, like salt. In these materials, the application of an electric field causes the positive and negative ions to shift slightly in opposite directions, creating a net polarization. Finally, we have orientation polarization, which is like a freestyle dance where molecules with permanent dipole moments align themselves with the electric field. This type occurs in materials like water, where the molecules have a natural separation of charges. Each of these types of polarization contributes to a material's overall dielectric properties, which determine how it interacts with electric fields. Understanding these different flavors of polarization is key to understanding the behavior of materials in various electrical applications. Section 5. Unmasking the math. Polarization equations made easy. Now I know what you're thinking. Math? In my cosmic journey? Don't worry, we'll keep it simple. The math behind electric polarization is actually quite elegant and helps us quantify this phenomenon. One key concept is electric dipole moment, which measures the separation of charges in a dipole. It's calculated as the product of the charge and the distance between them. P equals Q times D. The larger the charge or the distance, the stronger the dipole moment. Another important concept is polarization density, which measures the total dipole moment per unit volume of a material. It tells us how much a material is polarized in response to an electric field. Mathematically, polarization density is proportional to the electric field and a material property called electric susceptibility, which reflects how easily a material polarizes. P equals chi sub E times E. These equations might seem abstract, but they provide a powerful tool for understanding and predicting the behavior of materials in electric fields. They allow us to quantify the strength of polarization related to material properties and ultimately design better materials for specific applications. Section 6. Polarization in action. From touchscreens to saving lives. Electric polarization might seem like a hidden phenomenon, but its effects are all around us. From the smartphones in our pockets to life-saving medical devices, polarization plays a crucial role in countless technologies we rely on every day. Take touchscreens, for example. These ubiquitous interfaces rely on the principle of capacitive sensing, which exploits the change in capacitance due to polarization. When you touch a capacitive touchscreen, your finger acts as one plate of a capacitor, while the screen itself acts as the other. The glass layer of the touchscreen is coated with a transparent conductive material. This layer is polarized when an electric field is applied. When you touch the screen, your finger disrupts the electric field, changing the capacitance. This change is detected by sensors, which then determine the location of your touch. Another fascinating application of polarization is in the field of medical imaging. Magnetic resonance imaging, a powerful diagnostic tool, relies on the polarization of atomic nuclei within the body. By applying strong magnetic fields, MRI machines align the spins of atomic nuclei, creating a detectable signal. These signals are then processed to create detailed images of internal organs and tissues, allowing doctors to diagnose a wide range of medical conditions. From detecting tumors to visualizing brain activity, MRI has revolutionized the field of medicine, and it all starts with the simple principle of polarization. Section 7. The power of understanding, polarization, and the future. As we've seen, electric polarization is more than just a scientific curiosity. It's a fundamental phenomenon that governs the behavior of matter in electric fields and plays a crucial role in countless technologies that shape our world. Understanding polarization allows us to design better materials with tailored dielectric properties, leading to more efficient capacitors, faster transistors, and more sensitive sensors. It enables us to manipulate light with greater precision, leading to advancements in optical communication, data storage, and display technologies. The future of technology is intricately linked to our understanding and mastery of polarization. As we delve deeper into the quantum world, we're discovering new and exciting ways to harness polarization for even more groundbreaking applications. From quantum computers that leverage the superposition of polarized states to novel energy storage devices that exploit the properties of ferroelectric materials, the possibilities seem endless. By unraveling the secrets of polarization, we're unlocking a universe of potential, paving the way for a future where technology is limited only by our imagination.